welcome to our atomic structure unit. We're going to start this unit with a discussion of some of the experiments and scientists through history who put together our current understanding of the structure of the atom. So we all know that we now consider atoms to be the basic building block of all matter, or kind of the smallest indivisible particle that everything that we know is made up of. The idea that matter is comprised of atoms was actually first hypothesized by Democritus in 460 BC. The problem that we have with Democritus is, as you might know, he was a philosopher. So he kind of came up with this idea, but really didn't have any data or any research to back it. So he really didn't do any experiments. So he doesn't really have any data or evidence that matter is made up of atoms, or in other words, basically no proof. A lot of years go by. Because atoms are so small, we can't really see them, so it was very difficult to discover what is making up. So because the atomic world was so difficult to see, it was difficult to study, and we didn't really have a lot of evidence or proof at this time that matter was made up of atoms. So a lot of years go by before they really kind of have an idea that atoms actually do exist. John Dalton comes along, and this is really about the early 1800s. When John Dalton comes along, he discovers that water, for example, or any compound, actually has set ratios that it breaks down into. Each oxygen is identified to have a mass of 16, and each hydrogen is identified to have a mass of 1. So overall, water is considered to have a mass of 18. It's comprised of 1 oxygen and 2 hydrogens. He did find that you can separate compounds back into individual elements. If we do this with water, no matter how much water we have, there's always going to be a ratio of 2 grams of hydrogen for every 16 grams of oxygen. So you can actually kind of look and say, hey, every 1 oxygen has 2 hydrogens. He actually put together data. You can kind of see over here a rendition of what some of his drawings look like. He represented different elements with different little symbols and showed some of the compounds that they could combine. People bought what he was saying because he had a little bit more proof, and he had done some experiments. So the basics of Dalton's atomic theory say that matter is made up of tiny particles known as atoms. And he actually used this term to pay a little bit of homage to the Greek philosophers who already kind of had this idea. He said that atoms are indivisible. They're the smallest unit of matter. They cannot be broken down, created, or destroyed by physical or chemical means. All atoms of an element are identical and have the same mass. And something called compounds can be formed by combining atoms of different elements. Dalton's theory is a lot more accepted because he actually shows evidence. He does experiments, he presents data. There's some weaknesses of his theory. So matter is definitely made up of particles that we can also call atoms. These particles, in a way, are not exactly divisible, but there are smaller particles inside of them. So we now know that there are protons, neutrons, and electrons inside of an atom. So number 2 isn't really completely true. Number 3 is also a little bit problematic. We can have something called different isotopes. You may have heard of carbon-14 being used for radioactive dating. Carbon-12 is one isotope of carbon, and carbon-14 is a different one. So those are 2 atoms of carbon that have different masses. So we'll talk a little bit more about what it actually means to be an isotope and why number 3 is not completely correct. Strengths of his theory is, atoms are, what comprises matter. And the biggest strength of his theory was actually the notion of compounds. So the difference between an element and a compound and the ratios that are involved was very, very important, and really the strength of Dalton's theory. It was soon discovered that the world is made up of really small particles, and that even within those small particles, there may be a little bit more to the story. So we know that like charges are going to repel each other. Opposite charges are going to attract each other. And neutral charges don't really affect each other. They just kind of sit there. So based on this, there was this thing called the cathode ray tube. And the cathode ray tube and some related pieces of equipment were used for a lot of different experiments around this time. So the cathode ray tube is using a voltage source to send out a beam. And there's a positively charged plate and a negatively charged plate. As you can see, this beam is being pulled toward the positively charged plate. What you can deduce from this is that that beam is negatively charged. This is a picture of what a cathode ray tube looks like. There are a lot of different apparatuses with these involved with them. So if atoms are truly neutrally charged, and that's really all that's going on there, if you send out an atom and you send it through two charged plates, this is what should happen. In other words, it shouldn't be affected by the charged plates. It should take a nice straight path. So a neutrally charged atom should not be affected by charged plates. What J.J. Thomson came to find out in the late 1800s through his experiments is that when he actually shot a beam from a power source, he actually saw this. So what's actually occurring there is something is being pulled towards a positively charged plate. So what this tells Thomson is that within the atom, there is something there that has a charge. So it's discovered that from that power source, the beam that is emitted has something negatively charged inside of it. Further experiments show that beam had mass and was therefore actually a particle and not just energy itself. Other experiments around the same time, scientists like Eugene Goldstein and some others, some different details in this experiment, but what was essentially seen was if you change things up a little bit, you can create a beam of particles that gets pulled towards a negatively charged plate. So if something is being pulled toward a negatively charged plate, we can make the assumption that that is positive. So it was actually determined that there are, there's something positively charged inside of the atom at all. Now these are some gross oversimplifications of what we're actually going on with these experiments, but the basic thing that's important to get out of this is, we really have this concept of the atom being a small unit of matter that we get from Dalton. Dalton's atom didn't really have other bits or other pieces inside of it. These experiments start to show that even though you can't exactly easily split an atom per se, when you're looking at an atom, there are actually things inside of the atom that have different charges. So the atom does have smaller parts. It's not just like a hard sphere of mass. So based on the observations from the experiments, the scientists we've discussed began forming theories and making models to better understand the atom. Again, what's really, really important to understand as we go forward from this particular point right here is there are many, many people who are studying the atom and parts of the atom over time. The first two particles that are discovered are the proton and the electron. The reason that they're going to be discovered first is because they're the particles that have charge to them. Neutrons are not discovered yet. They're actually discovered significantly later because they're uncharged particles. And these, the types of experiments that are being run at this point were really based on the charge of the particles. There's a lot more to be studied and understood, and that's true even now. So even our understanding of the atom now has a lot of holes in it. So Thomson creates a model called the plum pudding model. Now, you probably haven't eaten a lot of plum pudding with raisins in it, but I also like to liken this to the chocolate chip cookie dough model. So you have a cloud of positive charge, it's kind of the dough, if you will, and within it, just interspersed through our electrons. So like cookie dough has chocolate chips just kind of, embedded in it. So in his model, he really has this mush of positive charge. He doesn't really have positively charged particles, and there really is no exact organization to where these charges are. So subatomic particle that's missing is we don't have the neutron yet. That has not been discovered yet. In terms of what's wrong with this model, we don't really have a cloud of positive charge, and electrons so randomly placed. So really, like, the charge distribution within this model is what's truly incorrect about it. So what happens next is we have this thing called the Gold-Foil experiment. Ernest Rutherford performs the Gold-Foil experiment in 1911. His setting was a lead block that emits alpha particles. Alpha particles are a positively charged type of emission that is actually a radioactive particle. It's not super dangerous, though. He had a piece of gold foil. So my source of alpha particles is right here. They're going to be shot out of here. He has this little plate right here, just helps focus them. And then we see this piece of gold foil hanging in this apparatus. Gold foil, if you imagine, is kind of like aluminum foil, only it's made of gold. And really would be even pounded even thinner. So very, very thin foil that's kind of the same idea as aluminum foil. Then he has this circular screen right here. And this has a coating so that he's able to actually see where particles hit it. So his expectation, if you imagine that you hung up a piece of tissue paper and then shot a gun at it, you would definitely expect that bullet to blow right through that piece of tissue paper. So his expectation is that all the alpha particles will pass straight through. So it is important to note going forward that the alpha particles do have a positive 2 charge. We'll learn a lot more about them a little bit later in the year, but they do have a positive 2 charge, and that's really important for part of what Rutherford saw in his experiment. So what Rutherford actually saw when he began to shoot these alpha particles through is that most of them do go straight through, but every now and then one of them would hit something and be blown off in a completely different direction, okay? And he called this being deflected. So this is another view of that. If you imagine that these are your gold atoms right here in the foil, most of the particles are going straight through, but some of them do have their path altered in some way. So most of the particles went straight through, just like he expected. And when we say most, it's actually almost all of them. Very few were actually deflected. If he had not been a good scientist, he probably would have missed those very few particles that were deflected, because it was really very, very few of them. So this leads him to 2 conclusions. Most of them going straight through means they didn't hit anything. That means the atom is mostly empty space. The fact that some of them got deflected is why we need to know these alpha particles are positive. There are dense regions of positive charge, which we now call the nucleus. So he kind of got us to this idea of, hey, positive charge isn't just spread all over the place like a dough. It's actually, in these little packets in the center, or, some in the center of the atom. And then around that, there's a lot of empty space, which we can deduce that's where the electrons are. I'll also include the link that you can see there. There's a really nice video about this. This is a very important experiment and is one of the experiments that you need to be very familiar with going forward. This was really a game-changing experiment in the world of atomic structure. So you really want to make sure that you watch that video and truly understand the impact of Rutherford's experiment. So based on this, Rutherford goes and makes his model of the atom, which is more of the solar system model. This begins to look a little bit more like what we're used to now. So he puts protons in the center, electrons outside, and he has those electrons orbiting kind of like planets. So most of the time when we make models, they're kind of based on things that we're already familiar with. So we get this solar system idea because people already had a pretty good idea of how the solar system was laid out. There's a problem with this. Orbiting is unstable. So if you imagine that centrifugal force, and you're going around and around and around, if you imagine like being on some sort of a merry-go-round or something, if you let go, you're going to go flying off. Planetary orbits are unstable over time as well. So the downside to this is this would make every atom inherently unstable, and atoms are not inherently unstable. They are inherently stable for the most part. So the fact that he has electrons orbiting was definitely a weakness to this. You would also expect, too, you don't really have anything preventing these electrons from just getting stuck onto the nucleus. So, you know, what's actually keeping those electrons in place? So Niels Bohr comes along next. He was a really important physicist who actually really contributed largely to our current understanding of the atom. Bohr discovers that electrons each have different amounts of energy. So we're going to do a lab where you actually get to see essentially what Bohr did. His model is very similar to Rutherford's. The difference is Bohr uses energy levels. So he says energy levels are like these little energy shells where electrons live, kind of like rungs on a ladder. And that energy that they have because of these levels prevents electrons from crashing into the nucleus. He still has them orbiting, essentially. So in this picture, we see, okay, we got these shells that I've depicted as rings, but the electrons are still traveling in these circular paths. So unfortunately, that's still pretty unstable. So, you know, we're not really done yet once we get to the Bohr model. Some of the things he did say were spot on, though. So Bohr did really help us come kind of a long way. Finally, we get to our current model, which is the wave mechanic or charge cloud model. It is important to note that around the late 1800s, early 1900s, is when Marie and Pierre Curie and Henri Becquerel discovered radioactivity. This really allows for example, the discovery of the neutron. So most of what we know about atoms now actually kind of came from a lot of their experiments. So the 1930s, the wave mechanic or charge cloud model was produced, developed. This is developed by quantum chemists and physicists. There's a lot of math involved. And in this theory, we say that electrons are in something called orbitales. Please notice that that's a very different word from an orbit. An orbitale is a region of high probability of finding an electron. And these look like these weird kind of clouds. So I have a little picture up here. If you actually imagine this is a picture of one electron. And imagine you have one of those cameras that you can just take a whole bunch of pictures in a row, like those cool sports cameras. So you have one electron, and you're just taking these pictures, taking these pictures, taking these pictures, and you lay them on top of each other. What you're going to see is this. It's the electrons moving around. Yeah, you get all these different pictures of it. But there is a region right here where you're more likely to find an electron. Then there's an area out here where you're less likely, and there's regions out here where there are no electrons. So when we say an orbital or a charge cloud, it just means that electrons actually never stop moving. They're just moving around in this little area all the time. And those are what we know as orbitals. So they're just these regions where we're likely to find electrons. They actually exist on energy levels, so Bohr was kind of right about that. Finally, in 1932, Sir Chadwick discovers the neutron. This took a long time because neutrons are neutral. So we weren't able to pull them towards a charged plate, which made the types of experiments these scientists were doing a little bit more difficult. Chadwick knew about protons and electrons. He knew about the nucleus. He knew that there was some mass that was not accounted for by protons and electrons, so there had to be something else. And his experiments actually utilized photons and utilized radioactivity to determine that the neutron was present. So this is kind of a little bit of a timeline for you to look at. This is not something that you need to worry about writing down, but it's very interesting to kind of think about the fact that, you know, we start in 1803 without even a concept of really atoms fully developed yet. And it takes until 1932 to even really have that idea of the neutron. You know, over about 130 years, we came to kind of the understanding that we're beginning to get to now, but it wasn't really very long ago that we just didn't know about this stuff. So take a pause for a minute, go ahead and answer these questions, and then we'll go over the answers. So the group of atomic models listed in historical order from earliest to latest. We start with hard sphere. Then we go to electron shells. The electrons are outside the nucleus. And finally, wave mechanic. What was concluded about the structure of an atom is the result of the Guilfoyle experiment. We have a positively charged nucleus surrounded by mostly empty space. Remember, we know that that nucleus is positively charged because it deflected positively charged particles. They're not attracted to one another. We have a bunch of models of the atom, and we want to know which one correctly describes the locations of protons and electrons in the wave mechanic model. So we can easily say first that we know protons are in the nucleus. In the wave mechanic model, we actually have electrons being located in orbitals, which are regions of most probable electron location. Number 4, which statement correctly describes the charge of the nucleus and the charge of the electron cloud? Our nucleus is positive, our electron cloud is negative. According to the electron cloud model, an orbital is a region of most probable electron location. They tried something tricky here. They want you to pick choice 3 because you say region of most probable, but we're not talking about proton location. Number 6, according to the wave mechanic model of the atom, electrons in an atom are located in orbitals outside the nucleus. So in our question about J.J. Thomson and Ernest Rutherford, after reading about the experiments and applying what you know, we want to state one conclusion Rutherford had that contradicts Thomson. It is important that what you put down, is conflicting from Thomson. So, you can't say, oh, there's protons and electrons in an atom, because they both knew that to an extent. So, a great answer to this would be that the atom is mostly empty space. Also, that the protons are in the nucleus, or something relating to that idea that your positively charged is not spread throughout. One aspect of the modern model of the atom that agrees with what Thomson said. So when we look back on what Thomson said, Thomson concluded that an atom was positively charged, so that's not going to work. And we have these negatively charged particles there. But overall, we kind of have this idea that the atom is electrically neutral. So that's really the best answer for this one. That overall, there's a balance of charge between positive and negative.